Hello everyone. Here is a problem that that will be an application of this particular definition we have been learning. This is the definition of static electric field, electric potential. So if you know the electric field, you can do the integration and you can get potential from here. And if you know potential, you can get electric field by just doing gradient of the potential. So these are related concepts, and it's only true for static. Okay, that's the review. So here is a situation. We have a metal sphere with a cavity. So there's a cavity inside here, and inside the cavity at the center sits a charge Q, and there's no charge, extra charge anywhere. So what will happen is when you place the charge Q, say this is plus Q, you will find that electrons will be attracted, and this end of the metal will become negative, and the surface of the metal, because this charge is moved over there, will be positive. Okay, so this, we say the metal is polarized. It's neutral. Metal is neutral, overall neutral. Same amount of positive charge, there's negative charge, no extra charge in the metal, but the metal charges have been separated. Okay, so we want to be able to get at this point what the potential will be, some point over here and some point here. Okay, so there are three unique points, and the reference is at infinity. At infinity, r equals to infinity, v equal to 0. So that's the formula we want for these 3 points. So if I want at p1, we'll go from the infinity to here. We'll do this integral. So we need to know at some point here, let's say this is if we want to do an integral, this is going radially out like that, so this is radial direction, unit radial direction, and then this is dr, so dl will simply be dr u hat. So if I knew electric field here, I could just take a dot product, right? And I can do this integral from infinity to this point rp1. But how do you get the electric field here? Well, you can use Gauss's law. So I will, you'll have to imagine a Gaussian a sphere of, say this is distance from here to here is r, and this is this little thing is dr at r. So this sphere is it's just a sphere in space, right? So Gauss's law applied to this is going to be 4 pi r square e, the rth component, the radial component electric field. This will be equal to, this is the flux through flux of the electric field through this surface, equals how much charge is enclosed over epsilon naught. Well, what is how much charge is enclosed? Well, there is a charge q, and then there is some charge here. Let's call it q minus q x, and this is plus qx. These cancel out, So they just naming it x, qx, qx, and then this one is going to be q. We'll find out that these guys are exactly equal to each other. The total charge here equals to actually the charge there, but we haven't found that yet. So this is just a total charge plus qx minus qx. So it just looks like a spherical thing. So over here, electric field is just q over 4 pi epsilon naught r square, and the vector is u hat r. This same direction, same electric field is u r hat pointed this way, electric field is pointed that way in this little element. So E dot dl is simply q over 4 pi r square, q over 4 pi square dr, and we need to have minus, and we need to from infinity to rp to point p, from reference to point p, and this is the integration variable now. So, and this is for that is infinity to rp, and this, if you work it out, it just q over 4 pi q over 4 pi epsilon naught rp. So this is the v at p with the reference at infinity. So that's the first part. So we got the question answer for this part. To get the p2, to get p2, let me erase, and because there are too many things over here. Okay, so to get electric potential at this point, we'll have to go from so this is infinity. I have to go all the way here. So electric field from here, we already worked out. Electric field was E in this area at some point was 1 over 4 pi epsilon naught q over r square u hat r. U hat r was pointed that way. So all the way I can go to distance. So this is a point A, that's the edge, and let's call this point B. So this is where metal is. So in here I have to go all the way here. So I need to know electric field in here. If you look at this integral, so I need to do this integral reference to P2. So this will be minus reference to point A, that's going to be 1 medium, minus A to point P2, right? That's the integral. I can separate the two. And this one is just like what we did for this point. So this integral is already gonna, we know it's gonna go q over 4 pi epsilon naught 1 over ra, and ra was given r2. So that's the same thing as outer surface. The same thing as r2. Now we need to do this integral, and so this integral, right, what's inside here is the same E dot dl. So we need to know what the, from here to here when I do this integral, so A to P2, this is A and this is P2. So dl is still dr u hat r. U hat r is unit vector point in that direction. But what is the electric field there? But this is a this is metal. So inside metal, in a static situation, electric field is static inside metal equal to 0. So this is going to be 0. Then integral, this whole integral will be 0. So V at P2 will simply be as if it got whatever the potential here is, it's going to continue like that. So V at P2 will simply be Q over 4 pi epsilon naught 1 over the outer cell radius. So that's the answer for P2. Now we want to know what's the P3 is an inside point, and let's work that out next. Okay, so we know this is equal to 0 in this area, and this we already know, and then to get the potential here, V at P3 is just I go from minus infinity to go all the way to A because it's one type of electric field. Then I go minus kind of add this to A to go all the way to B, this inside the metal, and then I go B to point P1, right? Now we already made sure that this is going to be 0, and this one, just this whole thing was simply Q over 4 pi epsilon naught. This distance is R2, this distance is R1. So you have R2, and B is at R1, but it's this thing is 0. This gives me 0. This whole thing is at the same potential. The entire metal piece is at one potential, because you can see that P2 point P2 is the same as this, any of these points, so this was the potential at V at A is V at B. Okay, and then I need to do this, so this thing integral I need to add. To do that, I need to know electric field when I go from B to P2. So I need to know I mean to do the integration around here. So in expanded way, this part I show it here. Here's the charge, here's P3, here's inside shell, this is the inside shell, and so this is dr. So dl here is again dr u hat r. U hat r is pointed this way, so radially. So if I point charge q here, and if I'm in a spherical thing, I use a Gaussian surface. So this is the Gauss's law. Use Gaussian surface using Gaussian symmetry, which will be correspond to over here spherical surface, and this is the distance little r for this. From here, from this Gaussian thing, electric field turns out to be 4 pi r square is q over epsilon naught. There's no qx minus qx, just q. There's no other charge inside here. So the E is actually q over 4 pi epsilon naught r square u hat r. Just formula looks similar, but it's a little bit different in terms of construction. So when I do this out, E dot dl is q over 4 pi epsilon naught 1 over r square dr. That's E dot dl, that's inside, and I need a minus of that, and I need to integrate from point P to point P1. So point B is the R1, this is the integration variable, P3, not P1 but P3, is P3. Okay, so I need to do this integral, and this is going to give me B at P3, not B at P3, it's going to give me this thing. So this I need to add to get you can see that this one, to add, you are going to be you are looking at q over 4 pi epsilon naught 1 over r. This minus kills a minus that comes from there, r1 to rp3, and so this is q over 4 pi epsilon naught 1 over rp3 minus 1 over r1. So this is same, and so the answer will be, if I put this thing inside there, q over 4 pi epsilon naught 1 over r2 minus 1 over r1 plus 1 over rp3. So you can see that it's not easy to guess without going through this whole calculation. This answer is not easy to guess. If you're trying to guess around, probably you come up short. So this is a very fundamental formula, and you can look at my previous video, go over that application. So let me conclude this. Is when you try to get electric potential, what kind of technique should you use in a problem? Okay, I'll just review that, and then maybe in the future problems you can use it. So we're done with this problem, but let's review some general techniques. Okay, so when you are trying to solve a static electric potential problem, you're trying to find a formula for it in a given situation. That depends on the situation, how you're gonna approach it. For instance, if you have a first question you have to ask is, do I have just the point charges only, or we have a point charges and continuous charges? What kind of problem do I have? If I have point charges problem only, then we can just do this. This is just using superposition of each of the formulas, right? So this is from each of the charges, and you just add them up. This is the summation, sum of this contribution for each of the charge. And it's very easy, and usually many problems are solved using this. Okay. However, if you have a continuous charges, or you have a both, the example we had was both. In our example, we had both point charge, and then you had continuous charge on the surface of these are induced charges on the metal, right? Here, this is the example we did, and in here you really have to do this, because you need to come from infinity to you got to find electric field here, electric field here, electric field here. Okay. So you find electric field in different domains if necessary, and then use this integral into different domains like we did here. And this is, all of this is only for the static electric field. If the situation is dynamic, say the source charge was, say this was source charge, and it was moving with a speed v, well, say even accelerating, right? Maybe acceleration is the same way. Then, because it's moving, not only gonna have here's electric field will be not only you have electric field, but you also gonna have magnetic field generated by the moving charge. Okay, it's kind of like a current generates magnetic field. So you're gonna have a situation, and if the magnetic field is time dependent, then then we say you have a dynamic situation. And for time dependent magnetic field itself actually creates electric field, and then it getting electric potential out of it is much more complicated procedure. Okay, so with just caveat, we're not going to do this for quite a while. We're just going to stay in the static for so maybe a whole month. Static electric potential, static magnetic field, and later on we're gonna, when we do Faraday law, then we're gonna enter the dynamics. Okay, till then this little flow chart should be very helpful to you in deciding which way you're gonna go when you attack a problem. Okay, with that, if you haven't subscribed to this channel, you can subscribe, and you can hit a like button. You can tell your friends about this channel. Maybe you can start a study group. When I post a problem, maybe you can attack it before looking at my solution. All of this helps. Okay, happy studying. Take care. Bye.